recording. So I posted all recordings, but I haven't posted the whiteboard notes for all of them yet. So I'm still working on that. It's I have to convert it. It doesn't just come as a PDF when I export it. So it's a process, but I'm working on that. So today's lesson number 13. And sorry, today's lesson number 12. And lesson 13, this is going to be, it's a little confusing because there's basically 14 lessons, but there's only one more day, 2 lessons. Because I do want to make Monday, there's 16 days, the 16th day is the final. I don't want to teach anything new on the 15th day. I want that to be a review day. So that day's, just not there. But then there was a day that I missed altogether. So I had to make a decision, and I decided I'm still going to do 14 lessons, but the 13th lesson, I compressed it to a 17-minute video. Although for some reason the 17-minute video is not. Oh, I see. That's supplemental for math majors. Oh, math majors, instead of doing a final project, you have all these supplemental activities, and I added a new one for yesterday's lesson and one for today's lesson also. So just be aware of that. Hold on. Those are pretty hard. So those of you who are math teachers and are thinking, oh, the math majors have it easy, they definitely don't. Hold on, let me make my auto lock better. So what I was trying to say is that by Monday, not only will you do the homework, because today's lesson is basically the second half of yesterday's lesson. So what was going to be, lesson number 13? So I want to do lesson 14 tomorrow. So lesson 13, I have compressed into a 17-minute video. I actually called it Cubics in 17 minutes. So you watch those 17 minutes, and it will teach you 2 algorithms that you can use to solve cubic equations. But if you really want to understand, what beyond just, I'm going to get this right on the final, but if you really want to deeply understand where these algorithms come from and why they work, you would watch this playlist. There's 2 videos, parts 1 and 2, that explain where these formulas come from. There's a part 3 to the playlist. That's for quartic equations, and that is something for the math majors to do. The math teachers don't need to go that far. And honestly, in these 17 minutes, you'll understand these 2 formulas. They're not very hard to use or to apply. They're hard to understand why they work. So lesson 13, the makeup lesson, is a 17-minute video, but there's a homework assignment with 4 questions based on that video. Okay, so that's a little bit of housekeeping. Oops. Let me do this again. I noticed in looking over the final exam that I'm still kind of putting together, stuff from yesterday and today is, there's a lot of questions based on yesterday's lesson and today's lesson. So you'll definitely want to study those up. Okay, and finally. Okay. Now, here's where we left off. We left off that Archimedes had a sneaky way of trisecting the angle, but it required a little bit of cheating, because we had to find the perfect point, wherever it is, somewhere around here, so that if you join this to this line segment here would exactly equal the radius. There's only one point that makes that happen, and there's no way to find that point with any sort of construction. So it's kind of a cheating thing, but it's interesting. And now I want to show you another Archimedes thing. if you are permitted to use other curves besides circle, and today's lesson is about other curves that the Greeks invented in order to solve the lesson 12 is just the other questions that were on last night's assignment, the ones we hadn't done. The first of the curves is called the spiral of Archimedes. This red thing. We'll define what that spiral is, because there's a lot of spirals, right? I can make all kinds of spirals that kind of spiral in different ways, but this specific one is special. With this spiral, you could accomplish both trisecting the angle and also squaring the circle. So this curve could be used to cheat to solve 2 of the 3 problems of antiquity, which is, a lot. If I come over here to lesson number 11, we see Greek geometry. That gets you the links to all these sketches, and among them is trisecting an angle with spiral of Archimedes. So first I want to tell you about what's special about this spiral, like how the points are defined. Let's see. There we go. Okay, here is how the spiral is defined. There is a radius that is moving around counterclockwise. Now, while the radius moves around counterclockwise, there is a point on that radius that is moving along that line itself. And the combination of those 2 movements creates a spiral. But to be more specific, when the radius has gone halfway around the circle, 180 degrees, that point is actually at the midpoint of the radius. And when it's at 90 degrees, that point is at the 1/4 mark. And when it is at 270 degrees, that this point on it is 3/4 of the way through. And finally, when it hits to 360 degrees, it's 100% through. And that's why in one turn, the point makes it from the center of the circle to the circumference of the circle.
This reminds you of the unit circle. This reminds you of the unit circle.
In the unit circle, we're often we have like the angle and sine and cosine tells you like where it's located. So this angle is, the point is defined by the angle. Now, so a question, just in case you're wondering, like, what is it someone could ask about this today? Well, I could say if the radius is 12 and this is 120 degree angle, what would the length segment of, I'll just call it AB? If I ask how long is AB, I actually, why don't I erase this part?
Would it be 1/3?
That's right, it's 1/3.
Yeah.
So you would get 120 over 360 is 1/3. 1/3 of
The radius.
1/3 is not the length, but 1/3 of what?
Of the radius?
Of radius, yes.
That's right. So the answer would be 4. That's the kind of, the final has about 30 questions on it. And this would be a question. This would be a perfectly excellent question to put on the final, because it's a question that would only take a few seconds to do if you know it. But if you don't know it, how the spiral of Archimedes is defined, you'd pretty much be in a lot of trouble on that question. So just think the final is, if you know the definitions of the things, the actual math will often be extremely easy. In this case, 360 divided by 3 is 1, divided by 120 is 3, or 120 over 360 is 1/3, and 1/3 times 12 is 4. Now, how is the spiral of Archimedes used to trisect an angle? And I think, let me just make sure, let me give you it. There is a Desmos activity, and it's FET4DR. Let me give that to you. So here's the Desmos code. This Desmos is just pretty great for remote teaching. I can see, eventually I have to go through these, and as for the class participation grade, which is 10%, I have to update my grades on that, to make sure that you're doing that you've been doing this. So like somebody who's not really here, they're just, they're on the Zoom, but they're also working a full-time job simultaneously or whatever, that person's probably not doing all the Desmos.
Professor, sometimes you guys move fast, so like I'm still solving and you guys say the answer. So like I just type it in because I was doing it on paper.
Yeah, that counts.
Okay.
You don't have to have all of them. It's
Okay.
There are people maybe who let's say they're absent for the day. They don't have anything on their Desmos that day, things like that. No, I'm not looking for perfection on these. You're just like, are you generally participating? You've heard stories about people that like, they literally worked 2 full-time jobs because they were on Zoom. They were like doing a halfway job on each of them, but getting paid full on both. It's hard when if you guys were sitting in front of me in a class, of course I'd be able to see if somebody was working a full-time job on the side while they were in class. Now, let me show you how you trisect an angle with the spiral of Archimedes. So you start with, in this case, the angle I want to trisect is one of the sides of the angle is the initial, is the initial radius, and here's the other one. This works. It's easier to see this if I'm trisecting an obtuse angle. So I have this 148-degree angle here. Now here are the steps. Step 1, find where the second side of the angle, not the horizontal side, but the slanted side, find where it intersects the spiral of Archimedes. That's step 1. Step 2, trisect, get this segment. See this blue segment? We learned as one of our constructions that you could trisect. So I'm gonna just go like that, 1, 2. Just gonna say we could do it if we wanted to, but for now we could just do it by just eyeballing it. But that is possible with a compass and a straight edge. Making the spiral of Archimedes, that's not possible with a compass and straight edge. But if somehow the spiral of Archimedes was handed down to us by God, then we could use the compass and straight edge to trisect this blue segment.
And that's dividing that line into endpoints.
Well, in this case,
analogy
3.
that-
In this case, that's right. But in this case, n is 3.
Okay.
So, but
Okay.
can I ask a question? So when we did that, we used the circles, right? To the radius of the circles, the 3 overlapping circles?
Oh yeah, so trisecting a segment, that like has its own, deal.
Right,
But let's just imagine, I'm not actually showing all the steps of that trisection. I'm just saying we could do it and then erase all the construction lines, and we'd end up with these 2 points. But yes, that itself would be a process.
okay.
But if I draw in all that, we won't be able to see what's going on.
Right.
Now, step 3 is to make a circle with center at the center of the big circle, but that passes through that first point. Step 4 is to see where that circle, that little circle, intersects the spiral. And the final step is to join the center to that intersection point. And that angle will be 1/3 of the original angle. Now, that's a lot. We're gonna talk about why that works in a second, but I do want to show you over here because you can see this better without the hand drawing. This lets you. Here you go. Here, take a look.
Before you move on, excuse me, hello. Before you move on, can you
Yes.
repeat the last step, please? Sorry, I was writing down the steps and I just missed that one.
Oh yeah, I'm going to show you like this. Here is trisect the segment. And here I just have the 1 point, the one closest to the center, because that's the only point I really need. Second, the next step is the circle. That circle has center at A and passes through that trisection point. And then finally, connect the center to the place where the small circle intersects the spiral. And you can see over here, the measurement of the 2 angles, 140.4, 46.8, exactly 1/3. And I could come here and I could change the original. Yes?
So we're drawing a line through where that little circle intersects the spiral.
Well, there's a point. One of the points is where the little circle intersects the spiral.
Yeah.
And the other point is the center of the original circle. Or
Okay.
what? There's 2 circles. So from the center of the circle to the intersection point.
Okay.
So the spiral is used twice. The spiral is used to find point B, or whatever this point's called. And then we use the spiral again when we intersect it. I want to give you a chance to talk with your neighbors now to answer the question, why does this work? I love that question. Now I have over here in here, you can draw the stuff, but type down here, you could say, if you kind of figure out, why does this process work? So let me put you into groups for a few minutes.
Before you cut us loose, did you say how you trisected the portion between A and B prime? Or double prime?
Yeah, I would have had to use that process that we did a few lessons ago.
Oh, okay. So the circles. Okay. Yeah. Okay.
Yeah, but for our purposes, we can just kind of approximate it. Just make a. So like I could just go like this. Okay, this thing looks around that big, and I'm not going to go halfway because I don't want to get at the halfway point. So I'll just go somewhere over there and just say that's 1/3 of the way. So we can approximate it, but you're right. In order to officially do this, we'd have to do the construction, but this is more theoretical now.
Right. I wasn't sure that's what you were meaning. That's why I just wanted to clarify. Thank you.
So let's have you talk with your neighbors to try to figure out what is it about this spiral that that makes this work. So let me put you into groups for that. How do I do that? Hold on. Breakout rooms. Okay, I'll make 6 rooms. 1 through 4 is the teachers. 5 and 6 is the majors. And put you in for like 6 or 7 minutes. Oh, I forgot to click open all rooms. Here you go. Okay, Arafat, do you have a room you want to get assigned to?
Yes, can you put me
Arafat, are you there?
yes, can you put me to the 5?
Room 5? Okay, does anyone from any other groups want to explain how that works? Why that's
We
a
have a
series of
theory.
steps?
My group, we had a theory because we were trying to figure out why the spiral trisect. So we kind of went backwards and was like, okay, if we want to model the angle, we just simply follow it, like mimic it. And then if we want to bisect it, we always make sure that the bisecting, that it was always half of the angle. And then we was like, when have we seen a spiral in nature like do anything? So we talked about animals hunting, and then we got into a very interesting perspective of planes. Like when we watch the movie Top Gun and we watch the pilot's dogfight, we see that in order for them to catch one another, they would have to like do these spirals to make sure they got around. And that was like the closest idea of why this works, that spirals happen in warfare, they happen in nature, and that's why this works.
Hey, Professor, building
Yeah,
off.
well,
Go ahead. I'm
there
sorry.
are times that, oh wait, I'll get my volume. Spirals do appear in nature in various ways, you know, because it's a combination of two motions, you know, a rotating and a moving outward. So yes, it does come up naturally. But what is it mathematically about about this spiral that causes it to happen?
Professor, our group came up with this. So you had indicated at the start of the lesson, the intersection between the radius and the spiral using the degree marker would tell you the portion of the radius that's underneath the spiral. Like in other words, 120 degrees gave us 1/3 of the radius. So what we thinking was by trisecting that portion of the radius, you're in effect trisecting the angle itself. It's like a double fraction, if you will. So that kind of apportions the angle by using the apportionment of the radius.
Okay, good.
And
Yes, there's something, and I'm just going to give an idea that might help you also think about it. What if I wanted to triple the angle instead of trisect the angle? I had a let's say I had an acute angle. You know, when I went from 1/4 to 1/2, I doubled the angle from 90 to 180, but I also doubled the line segment. Same idea. If I have like a small angle here I have like, well, a 40-degree angle. When I double it, it goes to a 92-degree angle, and the line segment gets double because they're basically proportional. The line segment is always proportional to the angle. So doubling it doubles the angle, tripling it triples the angle, and taking 1/3 of it will give you 1/3 of the angle.
Yeah.
It's real clever. Now, making a spiral of Archimedes, you know, you could make individual points on the spiral of Archimedes pretty easily. Certainly, you know, we have the 1/4. Sorry, that's not 1/4. We have, 1/4, 1/2, 3/4, 1. And I could easily make, some other points on it. And that's called in math a pointwise construction, when you're trying to make a curve and you can make as many individual points as you want on the curve, but you can't make all infinite of them. So because of that, we cannot make a spiral of Archimedes with a compass and a straight edge. Even point by point, there's just too many points on it. Now, the spiral of Archimedes is going to come back as a way of squaring the circle. But I want to stick with trisecting the angle and show you two more curves that can be used to trisect an angle. So I have on the screen a little line and a big line, and let's also put like a point underneath the big line.
I still have a question. How did they find the spiral?
Well, I would think that he would start by saying, if only there were a curve that had the property that the angle was proportional to the length from distance from the center. And then he would create he would basically, I mean, this is how I see it. He would create the curve based on wanting a curve with that property.
Interesting.
Yeah, visionary.
And hold on. Well, there are even crazier curves coming that were definitely made by first saying, I wish I had a curve that had this property. If only there were a curve that had this property, then they create a curve that has that property, and then that curve sometimes has other uses also. That's this one. This curve is going to be called the conchoid of Nicomedes. And I think first I'll show you what the finished product is going to look like. Give us some like motivation for what it is we're about to create. Conchoid of Nicomedes.
Isn't that like a bell curve or some statistical curve?
It does look a little bit like a bell curve. It's not officially a bell curve, but it does definitely resemble a bell curve. So you can see here the black curve. It's got like a bell curve looking thing. And underneath, on the bottom, underneath the line, there's that loop-de-loop.
Yeah.
That's called conchoid of Nicomedes. And it's not the only one. Depending on some sort of I'll explain about this other line. Depending on what it is, the conchoid of Nicomedes could look kind of like two kind of wavy lines, or in an extreme case,
Wow.
in an extreme case, it could actually look like a circle. See that? So in the extreme case, it looks like a circle. In the other extreme case, it looks like two wavy lines, but usually it has this shape, loop-de-loop on the bottom, and a bell curve looking thing on the top. It's a pretty cool looking curve. Isaac Newton once said about it that it's the fourth, most important curve that there is.
Now, curve on the top,
Circles.
Professor,
What's
the
that?
curve on the top look like normal distribution.
It looks a little bit like the bell curve.
Yes.
You know what? Hold on a sec. I must see if I can raise my volume of my speaker. Hold on a second. Let's see. Okay. Say that again just to see if my speaker's better.
Yes, I see that the curve on the top look like a normal distribution.
It does. It
Yeah.
does. It's not mathematically equal to it, but it resembles it it's kind of interesting. They're actually not connected, surprisingly. Now, here's how you get points on the conchoid of Nicomedes. This horizontal line is called the directrix. Okay. This point underneath is called the pole. And this little extra line here is called the distance. And I actually have, let's just take a look. How is this looking? Okay, so there's going to be some questions about conchoid. Okay, so here's how to get a point on a conchoid. It's actually very surprisingly easy. You go from the pole and you make a line segment towards the directrix. Or you could imagine, pick a point on the directrix and go from the pole to that point.
I'm having trouble hearing. Can you say that again?
I thought that was a student. I'm going to make this distance, I'm going to color it red. I haven't used it yet. So you go from the pole point to the directrix, and then you continue whatever this distance is. And that gets you an individual point on the conchoid. Now, if I picked a different spot on the directrix, like let's say I go straight up, and then I continue this distance, it's going to end up kind of higher up because it's, so this red line is congruent to this red line, is congruent to that red line. And if I keep doing this,
Is this perpendicular or no?
that one was. So with these points, these blue points have in common is if you connect them to the pole, the portion this portion that goes to the directrix will always be the same value. So let's take a look over here.
Wait, the green and the red will always be equal to the distance marker up above?
No, the green's different. It's
Okay.
just the red. So the green's different because depending on what angle I get to, you know,
Yep.
but the red's always going to be the same.
Gotcha.
So here we can kind of visualize this. I can move around this point. And you can see the 5.88. It stays the same. It's almost like a stick. Now EF changes for sure, but FG is always the same length.
So the perpendicular line will be the peak because that's the shortest distance between the E and the directrix, right?
Yeah.
That's right. That's right. If you go straight up, it's going to get as high as possible.
Yep.
Because you know, this red stick is at an angle now, you know, because I have to go from E to F, so it's
Right.
not straight up anymore, but it makes it straight up.
It's trading horizontal for vertical. As it-
Yeah. Yes, that's right. The smaller EF is, the bigger the smaller EF is. Actually, the smaller EF is, the smaller EG is.
Uh-huh.
Like, because EF gets bigger, right?
Yep.
But the height, it's kind of strange because it's not like EF gets bigger and EG gets smaller by the same amount. Otherwise, it would be just a straight line.
Yep.
But yes. Now you might wonder, what about the loop-de-loop? Oh, and what's neat about this is I could change the distance and see how I could get different looking conchoids. I also could move how far the pole is from the directrix. I could actually move it above it, get it upside down.
Is this connected to a parabola in any way?
No.
It's actually not connected to a parabola, but it does kind of resemble, all these curves can be used for, including the parabola, for problems of antiquity. So they do have some relationship to each other. Now you might wonder, what about the mysterious bottom branch? What's the deal with that? Well, the bottom branch with the loop in it is basically what would happen if when you went from the let me go over here. If I go from the pole to the directrix, and instead of continuing by the distance, I actually just turn around and go backwards that distance, that would get me a point on the loop-de-loop on the bottom. We usually don't use that loop-de-loop, but you know, you might be interested in it. So when I come back over here, you can see if I click on bottom branch, we can see both, or maybe get rid of the top branch if it's confusing things, and see this is the same idea. I'm just going from the pole to point F, but in this case, I'm going backwards by whatever the distance is, and that causes a loop to happen. Though not always. If the distance is small enough and the point is further enough away out, you may not get a loop. that bottom branch might not have a loop in it.
So I apologize. I think I'm very distracted by the graphics. Could you repeat how the bottom loop occurs again? The bottom branch?
Well, the bottom branch is if you go from E to F to get, let's start with the top branch, right? You go to E to F and then you continue whatever CD is.
Yep.
But what if instead of continuing, you turned around and went backwards that amount? Then you'd end up over here. So top branch, I go from E to F and continue going in that direction to get FG the same length as CD.
So
The bottom branch,
go ahead. Sorry.
the bottom branch, you go from E to F first, but then you turn around, head back towards E, and you go whatever this distance is, that amount.
Oh, so it's the differential? So is E?
Well,
is E?
yes, you subtract.
Yeah.
That let's call that point H. Oh, it is called H.
Yeah.
So EH is EF minus CD, and EG is EF plus CD.
Could you,
if you needed to know the length.
could you write that actually on the screen, please? Because that's a little confusing.
So to do that, let me just come over back to the iPad. Okay, so let me see. Do I have the other branch there? So let me say it this way. So here's the pole, and I think I was calling that E F G.
E, F, G.
And let me make this thing green. Whoops, that's cool colors. Oh, the fact that I could even use that means I did not turn on my. Okay, so I go to EF and then I keep going towards G.
Yep.
Or, and this is a little confusing because the distance is kind of big, or you go backwards. Whoops, get some red there. You go from here and go backwards that amount to get to H.
Yeah.
So FG and EH are the same length, which is the same length as the distance.
Yeah, there you go. That's what I needed. Thank you.
That H is going to be on the bottom loop. Now I have one of my favorite sort of final exam questions. Check this out. Oh, yeah. Look at this. Here it's conchoid. And my question is, what's the length of CI? And they told us 3 other facts. Sorry, I didn't put this into the, I meant to put this into the Desmos. It was supposed to be right between these 2 pages. I'm sorry, I didn't do that. So let me just put it up on the screen. So take a minute to think about that again.
So is it fair to say that EG is equal to FH?
Let's see, was that? No, EG is much longer than, wait, EG and FH?
Yeah, EG and F.
Pretty.
Because I thought you said EH is equal to FG.
Yes, I think it's correct. They are
Oh,
equal,
I
I
might
think.
be right. I've never, you know what? It's funny. I never tried to compare those 2 lengths. Let's put some numbers in.
Okay, all right.
Imagine the distance was 2, and imagine EF was 1.
So
EG would be length 3, and FH
Also be 3.
EF is 1. FH is just 2, right? Because you went from F and you turned around and went back towards the thing and you passed it. So FH is 2. FH and FG are equal because they're both, you either turned around, you either went forward by that distance or backwards by that distance. So that's true.
H is,
But as far as You were asking about EG versus what?
So F is the midpoint of GH then, right?
Well, that's true.
Okay.
Yes, it is. Because you went from F to G or backwards from F to H.
Gotcha.
That's right.
I'm just trying to
Now here
process it. So,
Well, I'll tell you, this question right here is the ultimate question for processing it.
okay.
I'm telling you 3 line segment lengths. I'm telling you that CG is 12. And that CF, I'll use different colors for this, is 5. And that CJ is equal to 10. So based on those 3 pieces of information, you are able to deduce the length of CI. Why don't you think about that for a minute?
C.
Yeah, take a minute to think about it, and then I'll have somebody say what their answer is.
J is 12.
Please don't shout out the answers, anyone.
Yeah, please.
Yes, let's give everyone a couple of minutes on it. Now, anytime you have a question of this sort, and this goes for any math problem, sometimes you have to say, okay, yes, they're asking me for CI, but what's something else you can answer that would be easier, but maybe leads us towards it?
What is the
And this
distance?
is some of,
What is the
that's right. And what is it?
7?
3.
Yes. This is 7. Because if CG is 12 and CF was 5, this must be 7. So where else must there be a 7?
From IJ?
IJ.
That's right.
Yeah.
This question is finished. The answer is 3.
Yeah.
So the line above the directrix, the line above the directrix, that distance never changes. It's only the line below
That's right.
the directrix that changes its distance over time.
That's right. So the key fact is that JI must be congruent to FG. That was the key, because that's what makes it a conchoid. So if you ever see a situation where you have a conchoid and there's a line segment, you know, like that, starting from the directrix towards, it has to be in, you know, starting from the pole going towards the directrix, but this portion above the directrix will always equal, that will always be equal. I love that question. Again, a perfect question for a test.
Right.
All it had in it was 12 minus 5 is 7, 10 minus 7 is 3.
Right.
But
Can I-
of course, it's
can
a
I
hard
ask you-
question.
Can I ask another question, Professor?
Yes?
If you were shown the conchoid curve, which I'm assuming is the curve above the directrix, right? That's the conchoid curve. But
Yeah.
you weren't shown anything else, and they said, I want you, where would point C be? Is it always just directly perpendicular from the top of the curve downward?
Well, yes, except we don't know how low it goes. So you're right, C is definitely on this perpendicular, but
Right.
depending on how high or low, how much below it is, you get a different curve. So no, I don't know how you would, I don't know how you'd figure out where.
Well, you know, I mean, you would know the distance, right? From the directrix to the top of the curve.
Yeah, but John, doesn't that
Yeah, this is,
define the upper curve? It doesn't really define the lower branch, right?
oh yeah, I don't know, I mean, yeah, we really don't need the lower branch. But I'm thinking if I went from the top and went perpendicular, I would know that the thing was on that.
Right.
And then but now I'm stuck because yes, this distance is the same, but it's not like I could pick some other point and like I'd have to figure out what angle to go at so
Yeah.
that this distance was equal to that distance and then the
Right.
intersection. So no, there's no way to find the pole.
Okay.
In
No
fact,
easy way that I know. of.
that upper curve is really defined by the distance between the directrix and itself, right? That 7. It's just as it's leaning down, it starts to spread out. I have a question though. It looks like it goes forever, but is that not true? Because there must be a limit to how far 7 can come down, right?
Now it goes on forever because if I make practically 180-degree angle,
Yeah.
it will still go above that line.
Ah,
But
gotcha.
once this becomes parallel
Yeah.
to the directrix,
Yep.
then there would be no point.
Okay.
And if it's going more than parallel, it's not hitting. If I'm going array, it's not hitting the directrix at all.
Gotcha.
But no, it's a infinite. It's got asymptote.
So to have the whole
Now
diagram, you must have the pole. You must have.
you got to have both the pole and the distance.
Yeah.
Now the conchoid of Nicomedes can be used to trisect an angle, but it relies on an obscure theorem. Okay, the obscure theorem is this. If you have a right triangle, why is that saying 4.5? I meant to call that 9. Here's a right triangle with hypotenuse 9. Now, if I find the midpoint of that side, BC, I'll just call it D. It will split the hypotenuse into 2 equal pieces. And here comes obscure theorem. It's kind of surprising. If I join A to D, that's the median. That's what it's called. It turns out that that median is also going to be 4.5. So obscure theorem, length of median drawn to hypotenuse is equal to 1/2 hypotenuse. I think if I come over here, I probably, let's see, trisecting median here, median drawn to hypotenuse. No, that's where the 4.5 must have come from. Here's the median, and as you can see, this was 4.5 and the median is 2.25. If I change my triangle, the median drawn to the hypotenuse always seems to be equal to 1/2 the hypotenuse.
Wow.
Add that to your list of obscure theorems. Surprisingly, it has a very easy proof, and here it is. Bonk. That's the proof.
Professor, does that mean
Yes.
that triangle will always be an isosceles triangle that is formed?
Yeah. See,
Okay.
the proof is the reverse of Thales' theorem. If you made a circle around remember, a semicircle always makes a right triangle when you right angle. So
Yeah.
that means if I put a semicircle around a right triangle, if I put a semicircle around the right triangle, the BC will end up becoming the diameter. But AD is going to end up being the radius because D is the center of that semicircle now. So it's a very slick proof of why that works. But it's sort of an obscure theorem. Like, I mean, they teach it in geometry, but it's a very forgettable theorem. But it's important because we need it for the very important thing we're about to look at. Here I have a diagram. And this diagram, oh, and by the way, if I come over here as an exercise, it's hard to do this. Circle which 3 points would be on the directrix. You'd have to try to say which of these points, if I joined you know, G to the pole, you know, would this distance equal that distance? This is much better done if we have it on paper, so don't worry about that question. But here's a very important question. Here is a geometrical picture, a triangle with a lot of lines in it. Let me make this a little bigger. Okay, here are the facts of this picture. Oh, I think I like better what I wrote on this. 2 TE equals 2BC. Oh, it says exactly the same thing. Oh, if ABC is 60 degrees, what's ABD?
ABC.
So I'm telling you that this is a 60-degree angle. Oh, and this is a right angle. And they want to know,
30.
their question is, in this picture, here's some more facts. You know what, I'm going to put some numbers here. Can I just say that BC is length 10, just to make this a little more concrete for us? BC's length is 10, that's the hypotenuse.
AB
And-
should be 5.
A what?
AB should be
AB.
5.
Oh, yeah, that's true. It's half. Let's pretend we don't know that just because we don't need it. And if this was like 70 degrees, we wouldn't know it at all. So, but you are right. Let's change this to 63 degrees, so that that's not even an option. I don't want you to think this only works for special triangles. Now they're also telling us that DE is 2 times BC. So DE is 20. These two lines are parallel. And this is a right angle. And the question is, from all this, can you figure out the measure of angle ABD? That piece right there. ABD, sort of the lower sort of portion.
We don't know if line BE is bisecting angle CBA, right? So we can't say that we would know DBA or DBC.
That's right. We don't know is this angle bisector. All we know, this is all we know. We know that this angle is 63 degrees. This is 10. This is 20. M is the midpoint, and the lines are parallel. So even though they're asking about angle ABD, is there anything in this picture you could say, you know, a length of a line segment or anything?
Well, based on our obscure theorem, we know CM is
Good.
half of DE.
Yes.
That's right. CM is 10 by obscure theorem. That's going to be really important.
We also know angle BCA.
Yes, we do. We can put that in. I'm not going to put it in because we don't need it, but you're right. We can say that it's 27 degrees. Okay, any other things we can say now?
Well, no, that's huge because of the triangle angle sum theorem, right? If we have a right angle in 27, we can tell what BDA is. That's huge.
No, what would, if that's 27, we don't know, like if we have this 27 here, where do we go with that? This angle down here is not part of that triangle.
Yeah, you're right, sorry.
Let's, I am going to call temporarily the angle that we want to get eventually. I'm going to call it angle X. Are there any other angle X's in this picture?
CEB.
CEB? That's
Yes.
right.
Yeah.
This is the
Alternate
parallel
interior
line.
angles. Any more X's in this picture?
BCM because of corresponding. Am I right about that?
No, BCM looks like it's bad. It's like obtuse angle maybe.
ECM.
ECM by what reason?
They're isosceles.
No, they are equal.
That's right.
Yeah, I mean,
You're right. It's isosceles because remember, we had the 10 here, but we also have a 10 here.
Ah, and we know what that is, don't we?
We know what is.
Oh wait, I just had it. 20, but we have two no, that's not it. Sorry.
That's all right. Now, what can you say about a mysterious angle? This one right here.
Oh, isn't there an alternate interior angle on BC? Because if 63, right, ABC is 63, what's not included in BCE is going to be the difference between 180 and 63, right?
Yeah, if I were to extend this line,
Yeah.
I could, but like put a 63 here, but it's not going to help me.
No, okay.
Well, we know angle CME, right? Which is 180 minus 2x.
Right?
Yes.
And so if 180 minus 2x, and then we know CMD, because you have to add, that has to add up to 180 with CME.
Yes. So what can you say about that? CMD.
Is to
That's the
x.
key actually to the question.
Is to x, I think.
Yeah.
It's 2x.
Yes.
Now the best way to get that is exterior angle theorem. Because CMB is the exterior angle to this skinny triangle. So 2x is the sum of the two remote interior angles. Now there is, so we worked with this isosceles triangle, but there is another isosceles triangle. So what conclusion can you make now? What can you fill in now that you couldn't fill in before?
So the
CBD is also 2x.
yeah.
That's right. Isosceles triangle. See, these 10s are all over the place.
Yeah.
So this is also 2x. Well, check it out.
So
Look what happens.
That trisected the angle.
3x equals 63 or x equals 21.
very cool.
So if you could ever create this picture, you can trisect the angle with it. But this picture is pretty hard to create. And here's why it's hard. So it's a hard picture to create. And let me see if I have over here trisecting angle with conchoid. Yes, this is very nice for demonstrating this. You'll see why. In order for this picture to work, I'm not drawing the median right now. The key thing about this picture, the key thing about here, and let me make a copy of this thing and put it onto a new page because it's getting kind of messy. It was critical that DE was double the length of BC. That was critical. If that wasn't true, this whole thing would have fallen apart. So if I have triangle ABC and I extend and I make this big long ray that's parallel, I need to find point E. Most of the places you try to put E are going to be wrong. Let's say I think E goes here. How could you verify? How could someone say, no, actually, you're wrong? What would they do to prove that I was wrong? What with their ruler? How could they check if E was in the right spot for this diagram?
Well, they'd have to measure what BC was and see if BE is double that.
Yeah.
If what is, so they measure BC and they'd have to measure what?
DE.
That's right. So if this was 5 and this was 8, it's like, no, E is in the wrong place. Check this out. I can come over here And I could actually move, I called it H in my picture, but check it out. So most of the times when you put where you put that point, it's not right. And angle EDI is not 1/3, but check it out. You see here, IH is 4.15, and here it says 2 times DF is 9.05. So if I keep moving it, see IH is getting bigger, it's getting bigger, it's getting bigger. See the ratio of EDF to EDH is 1.94. Keep moving H out, keep moving H out. IH is getting bigger. It's getting closer to 2DF. It's getting closer to 2DF. It's getting closer. And then finally, it reaches it. When H is in the perfect spot, IH will be double 2DF, will be double DF, and the angle will get trisected. EDH will be 1/3 of EDF. Any other place? It's not true. So finding point H is the secret. What's cool about this is that you can change the initial angle just to kind of mess around with it and see. So the big mystery is, where does H come from? And I'm going to show you where H comes from. And then I'm going to have you talk about it in groups for 15 minutes. It's a very hard question. Here, H is in the wrong spot. And now, get ready to have your mind blown. There's a sideways conchoid, which intersected the parallel line at this point G. Check it out.
So is FIE the directrix?
It is. That's what I want you to talk about in groups, though, for a few minutes.
Okay.
What's the story with this conchoid? What conchoid has 3 things: a pole, a directrix, and a distance. What are those 3 things to make this is like the perfect conchoid? What defines it? You are right. FE is the directrix. Okay, I'm going to put you in groups now to talk about this. Let me see. Do I have? Is it in here? Let's see. Yes. So can you, on this page, explain what's the deal with this conchoid that caused us to get the perfect point so that the angle would get trisected? This is one of the great questions of the entire course, in my mind. So let's give you like 10 minutes to talk to your neighbors about it. What's the deal with this conchoid? How was it made? So I'll open the rooms now.
Professor, I had a quick.
Yeah,
If you take the median of FE, right, and then you connect a line to
FE?
yeah, so we have the
You mean
director.
the midpoint of IG?
No, the midpoint of FE.
Oh, is it,
And does it
from
the line extended from the midpoint to FDE? Does that bisect the angle?
oh, the median?
Yeah.
No, you
No.
know, in general, the angle bisector is not the median. You know, like yesterday we did the angle bisector theorem, and in general, it does not split the thing into two equal pieces unless it happens to be a isosceles triangle. So generally, no, and definitely not in this case.
Not in this case.
Because so what was the story? First of all, do I have? Is it over here? Yes. Okay. Was anyone in their groups able to identify what's basically the three components of this conchoid? How was it made? Let me go for a volunteer, and then I'll call on someone. So do a hand raise in the. I could see it in the participants. What's the story with this? There's three things we have to know. What's the pole? What's the distance? Okay. Yes. So Braulio.
Yeah.
What are the three things?
Okay,
Pole,
so the pole
directrix.
is D. The
That's right.
directrix is the line FE.
I'm going to
And
extend it.
yeah, and the distance is IG.
Yes, it is, except we wouldn't have IG yet because
Okay.
we wouldn't know where point G was yet. But you're right. The distance does equal IG. That's true. What if I didn't have the conchoid yet? Because remember, you wouldn't have point G yet. Let's say all I had was this right triangle. And I said, okay, make the, find point G by making the conchoid. And you said, okay, I'm going to make this the pole. And I'm going to make this the directrix. But I don't know where to put G, so I don't know how long IG is. So there's also another answer that's going to be better for our purposes. IG is true, but it's not, I should have made this more clear. If I didn't have point G yet, and I wanted to make this conchoid, I wouldn't be able to.
But we do have point D, right?
Yeah.
So we have
All we have is 3 points, D, F, and E.
So wouldn't you take FD and double it based on what we just practiced using that?
That's right.
Define G?
That's right. That's the answer. You make the distance to FD. Now, if you do that, just because what's not shown in this picture is if I go from D and go in any direction, and then I continue, actually, why don't I make it green and red? This length will be 2 FD. And if I go in some other direction, that'll be 2 FD. So all the points on the conchoid.
Why is that?
The point that's really important is the one that that intersects with this horizontal line here. That's just another point on the conchoid.
Yeah, but is that a special?
But it's a really,
it wouldn't be. I mean, FD is going to be shifting based on where you're going along the conchoid, right? So is this a special case? This particular setup?
well, by
Because
making it 2 FD,
Yep.
and so every point on the conchoid is going to have that property, including
right,
this one that intersects the parallel line. But
right.
what's good about that is that now I have the diagram that I needed.
Right. But I guess my point is this, right? That those lines are going up and down, you know, at all different angles, hence the different shapes of it. So if you moved F out further, that would no longer be true, right? So that, I guess, is what I'm getting at.
Well, if F was different, the conchoid FD would be bigger, and you'd have a different, you know, looking conchoid.
Oh,
So I can actually show you that. So this conchoid is going to look different here.
okay.
If I come over here. So the conchoid will depend upon the length of FD. So
Yep.
check it out here. I'll move this to the edge.
Yeah.
And if the angle was different, see, the conchoid would get different also. But the key is the distance would, if you had a tool that made conchoids,
Yeah.
you would set the distance to 2 times FD. And then you would see where that intersected the parallel line. And that would give you the mysterious point G, which would give you the picture that you need. So conchoid does that. There actually is a tool that makes conchoids. Let's see, tool that makes conchoids. Here. Is that? I don't know. That's not a picture of the tool. Here we go. Conchoid definition. Yeah, it's got some conchoid here. Nicomedes conchoid mechanical device. See this thing?
Mhm.
It's got like a ruler thing, and there's like a, I don't really know exactly how this works now that I'm looking at it. It like, that's not a good picture of it. Oh well. Okay, it's break time. When we come back, we have 2 more curves to do. We've done the conchoid and the spiral. Today is 4 curves. The third one's called the quadratrix of Hippias, and the fourth one is the parabola. So 2 more curves. We did 2 before break and 2 after break. Take a 10-minute break now.
So Professor, that is a general law. The FD will always be half of the distance.
The distance, yes. I mean, general law, meaning if you're trying to trisect an angle,
Okay,
you won't, that's the only way to accomplish it.
okay,
Right? I can make all kinds of conchoids,
gotcha.
but it won't create that. If I pick any other distance, I'm not going to be able to do that proof because these 3 things will be equal,
Right.
but this one won't be.
Okay, so that's what I
And
was.
then I won't get this isosceles triangle
Right.
that
Okay.
I needed to put the 2x there.
So it's a special case then. This is a special case where there's this exact arrangement. That's what I guess was trying to ask earlier. You have to have it.
Yeah, there's only one. If the goal is to trisect an angle,
Yep.
you have to choose, just like with all our constructions, you know, you have to make this circle this size or put the
Yeah.
position here.
Yeah.
In this one, it's like a construction.
Yeah.
You know, construct a conchoid. If you choose to make it so the distance is 2 times FD,
Yep.
then that magic point will be the endpoint of the, you know, the trisection.
Okay, that's what I.
But if not, it won't be.
That's what I was trying to figure out. So that's awesome. All right, thank you.
You know, you don't even need the that extra line. You know, once you do this, it's done. This is the angle now.
Yep.
Theta over 3.
That's awesome. All right, cool. Thank you.
Okay, you're welcome. Okay, so see you in a few minutes. Okay, everybody, welcome back. Now, there are two more curves we're going to look at today that are important in history and math. And the next one you can see on your screen. What you see on your screen is a square, and the green thing is a quarter circle. But that red thing, which kind of looks like, it looks a little bit like a piece of an ellipse or something like that. That curve is called, whoops, that curve is called the quadratrix. Quadratrix. It's actually hard to say. Quadratrix of Hippias. Most people just call it the quadratrix. The word quadratrix, by the way, the word conchoid is was Greek for like shellfish, mussels, like the kind of shellfish, because it looks a little bit like one of those animals, I guess. But the quadratrix, the name quadratrix, comes from quadrature, which basically means it's used for squaring the circle. Squaring the circle, quadratrix of Hippias. But it actually can also be used for trisecting the angle. And the conchoid of Nicomedes could be used for doubling the cube. So these curves and the spiral of Archimedes can be used for squaring the circle. So each of these curves can be used to solve 2 out of the 3 problems of antiquity. So now the question is, how is this curve defined? And it's defined a lot like the spiral is defined. Let me show you what I mean by that. It's defined by 2 motions happening. So here it says quadratrix. Full screen. Okay. So this, let me just move this, make this bigger. So check it out. There is a radius of the circle that is starting as a vertical line segment, and it works its way clockwise down till it ends up at being horizontal. Oh, here we go. Now at the same time, at the same time, there is a horizontal line that is making its way from the top of the square down to the bottom of the square. And notice how they're racing. Who's going to get down to the bottom first? Point F or point G? They end up getting there at exactly the same time. So when the angle is 45 degrees, ABG, when that's 45 degrees, this line will be it's half of 90. So the line, point C, would be halfway down. When I'm at, let's say, 0.66, here I'm 2/3 of the way around. ABG is 60 degrees, 2/3 of 90. Point G would be 2/3 of the way down from would be 2/3 of AB. And it continues like that. We're going to practice this a little bit. There's questions that we can do with it, but that's just the basic idea. Very similar to the spiral, except in the spiral, there was a point on the radius that was moving. And here there's this sort of point that's moving down the other radius, but it's making a horizontal line, and that horizontal line. So just glance at that for a bit. Now to see that you understand the conchoid, I'm sorry, the quadratrix. Hold on. here's a picture of a quadratrix. That's like, I'll just go like this. Sorry, this should have been a question in the Desmos. So imagine that the entire side of the square was 24. And I told you that at this moment, sorry, I don't want to make it 24. Let me make it a multiple of 9. Eraser. If this was 27. And this angle down here was 20 degrees. My question for you, and here's the point on the conchoid. My question for you is, how big would this length be from here to there? Okay, I want to give you a minute to think about that. The question is, this point came from seeing where this diagonal line intersected the quadratrix and just making a parallel horizontal line. So to see if you understand the quadratrix, take a minute now to ponder how big is that segment that's identified with an X. I'll give you a few minutes to think about it. Now we're not getting the answer yet, but any question that's like this, it's like, X. Is there anything you can get? Maybe it's not X. Maybe it's something easier for you. And maybe that thing is going to be the bridge between these two pieces of information. So what's something we can get that's not X that we could get easily? Well, you could raise a hand for that. What's something we can get, even if you think it seems trivial? What's something that we can get? Scott? Or Christina?
So
I
the
was
other
gonna say, if
angle,
you're the 0 marker, the 90-degree marker, it's the full length of the radius, so it's 27.
70.
So those we know, right?
Yeah, and Christina, what were you going to say?
The other angle that, the angle A, can you hear me? I'm sorry. So it's 90 minus 20 is 70.
Okay, that 70 is going to be important.
Mhm.
How so? Still, Christina?
Well,
What'd you
if
get for your answer for X?
I got, what is it, 70% of 27, 18.9?
It's not 70%. Oh, it's not 70% of 27, but you're on the right track.
Okay.
Not 7, because that angle is not really a percent. It's not, it is almost 70%, but it's actually not 70%.
It's 70
Grant?
degrees over 90 degrees. Makes 7/9 times 27 is 21. Is the way I did it.
Okay.
That's right.
70 out of
So
90.
7/9 of the, so 70 out of 90 is 7/9.
I
So
did it.
7/9.
I did it
It's
differently.
gone down 7/9 of the way, which means this has also gone down 7/9 of the way.
Very cool.
7/9 of 27.
Professor,
I
I
love that
used,
question.
I used the 20-degree angle. I said 20 out of 90 was 2/9. I took 2/9 of 27 was 6. So I said A
Good.
to the green point was 6, and so X must be 27 minus 6.
That's great. 20 So you said 20 over 90 is kind of what's left.
Right.
That's what remained. And 2/9 of 27, 6. And then you did 27 minus 6 is 21. I like that question. These make for very good final exam questions because somebody who understands the definition of a quadratrix, the math involved was just 70 over 90 times 27 or 20, 27 minus 20 over 90 times 20, or but if someone doesn't know what the quadratrix is, they have no possible way of answering this question. So I really like that question. And I think I have a question like that on the homework. Here's a question I like also.
Before
Check out this one.
Can I just ask a question before you move on? So, but if you go all the way to the bottom, isn't the radius still 27? So that would be 0 over, right? Or I guess I'm saying vertically, right? So if you're vertical, there's
Oh, I hear what you're saying. You're saying, what about when I get to the very end?
right.
What about when I finish? That actually would be so when I finish, this angle would be basically 0 degrees.
Right.
And this angle would be 90 degrees. So yes, it would be 27. 27 would be the length of this vertical line segment. It's the entire side of the square. It's not the length of this. That's its own very difficult question.
Right.
But yes, if it got to the bottom, the answer would be 27 because this horizontal line would have made it all the way down to the bottom. So this vertical line would be 27 in that case.
So what is the length of the horizontal part then? It can't be 0, can it?
Now the horizontal is very difficult.
Okay. So
The
this
horizontal line, we're going to talk about that. Yes, it's the horizontal line. That one we don't know. I mean, we could use trigonometry for it,
right.
but if they don't have trigonometry, we can't. We could do tangent of 70 equals x over 6. So yes, we could figure out that horizontal line segment.
But not with the quadrant.
But yeah, that's going to be important for later.
Okay.
Now here's a really good question also. It's on here. Here are I have 1, 2, 3, I have 6 points. F, E, D, G, H, I. Can you somehow use those? I cut CA into fourths, and I cut arc CB into fourths. And my question is, can you use this? You could draw, right? You could draw on this. Can you produce 3 points on the quadratrix from this picture? How would you do it? So everyone take a minute on that. That's a nice question also. Only 3 points can you get on the quadratrix from this information, but go ahead and do that. I'll take a look at the you're going to have some auxiliary, so you're going to have more than just the 3 dots.
Is it safe to assume the distance and the pieces of that circumference they're equal? Like they're each a fourth?
They're each 1/4. Yes. So this line segment CF, FE, ED, DA are all 1/4 of the square's side, and the arcs CG, GH, HI, and IB are all 22.5 degree angles. That's that arcs. That's right.
Okay, thank you. And did you give us the side of the square's length, or no?
You don't need it. So
Okay.
no, I didn't give it to you.
Okay.
Okay, so I'm looking over your answers now as you draw. So far, I see 2 correct answers and 6 ones that are not totally correct. So it's okay because that's why we're practicing this. But I'm just noticing most of the answers have some inaccuracy in them. Now yours might be right. So don't necessarily change yours. You might have changed, yours might have already been perfectly right. And a lot of people, even ones that are wrong, know that there are 6 lines that need to get 3 pairs of lines that need to intersect with each other to get the 3 points. But I see a lot of different answers. I see, it's interesting to see all these different answers. Currently, only 2, 3, only 3 are correct fully, and I see some interesting other ideas that aren't quite correct. I anonymized the names, but I'm going to show you what all our answers look like. Your name is not on your thing. Take a look. See all these different answers. So this one is not correct. The horizontal lines are correct, but the vertical lines are not correct. This one is not correct. The diagonal lines, the radii are correct, but FG, EH, and DI is not correct. And here's one that is correct. See, they have horizontal lines. Ooh, they use the line tool, I think. They use horizontal lines for the starting at F, E, and D. And they used the radii going to G, H, and I. And they intersected the horizontal line from F with the radius going to G. That's the 22.5 degree mark. Then the horizontal line through E and the radius to H, that's the 45 degree spot. Then the horizontal line through D, this is 67.5 degrees, and the radius to I, 3/4 of the way. So that was an interesting question because you can see how many different sort of ideas there were. They're not bad ideas. They just weren't accurate. So here was the ones that this was off, though not, it's not like such a bad idea. And this one was also off. Again, not a terrible idea. But the correct answer, again, is this one. Horizontal lines intersected with radii. I like that question also. Okay, let me bring back the iPad. So again, the process was, it's kind of confusing because this H looks like the vertical line with that made 1 point. Vertical line with that made another point. Sorry, horizontal line and horizontal line with that.
We can't see your drawing.
Yeah.
Yeah.
Oh, Thanks. Let me do this again. Horizontal line with this radius, horizontal line with that radius, and horizontal line with that radius. So just these 3 points. Now, the quadratrix, although its purpose was to square the circle, I want to show you how it could also be used to trisect an angle. Okay, so here's the way it works. To trisect an angle with a quadratrix, I think I'll go full screen on that. Okay, so here I have an angle I want to trisect, angle DBG. And I have this, so here. Here's my angle, DBG. And somehow I have a quadratrix also. So I find where the quadratrix intersects the side of the angle that I'm trying to trisect. And I do this. You know, I'm going to do this on a separate page because it'll be easier to understand. Let's come over here. Let me grab this guy. So here's the angle that I want to trisect. Step 1, see where that, not the horizontal side of the angle, but the slanted side, see where it intersects the quadratrix. Step 2, make a vertical line from that point. Step 3, trisect, just like we did with the spiral, trisect that line segment. Yes, that would be like its own process. Step 4 is make a horizontal line. And wherever that crosses the quadratrix, if I go from this point to that point, it will be trisect angle. So again, the steps were, where's the angle across the quadratrix? Vertical line, get the 1/3 point on that vertical line, move over horizontally, and that point becomes the end point of the other segment that makes the trisected angle. And I believe I can teach you why this works right now also. I'm going to go like this, 3x x. Because I trisected the line segments. But because the angle is always proportional to the size of this line segment, because it starts off as a 90-degree angle, and that line segment is full. And as the line gets cut in half, the angle gets cut in half also. So when the line gets cut in a third, the angle gets cut by a third. Actually pretty confusing. It has to do for the same reason as the spiral. The angle is always proportional to the length of this line segment. Because as that line segment goes from full down to 0, the angle goes from 90 down to 0. So when a line gets cut in half, the angle gets cut in half. And in this case, the line gets cut by 1/3. So the angle would also get cut by 1/3.
So the horizontal line and the vertical line guide you to the quadratics for the trisection.
The horizontal line is important because without it, I can't get this point right here.
Right, that's. what I was-
Yes. That's right. So the horizontal line gets you onto the quadratrix, which you need to be because that quadratrix has a special property that any point on it, this line segment is proportional to the angle. Sorry, this line segment is always proportional to whatever angle this makes.
Right.
So that's the idea behind it. It is pretty confusing, that one. Like, to understand why it works. But why don't you come over here and at least do the steps? Oh, actually, this is a question. If KAE is 60 degrees, what would the measure of angle KAI be? So this is a real quickie. They tell us that GH is 1/3 of GF.
Wait, what? Can you go back up to the top?
Yes, maybe you know what, I might be able to zoom out a little bit so we could see it all at once. Here we go. So GH from here to here is given as 1/3 of GF. And they want to know how big is angle KAI. If it's given that KAF, KAE that is, that angle is 60 degrees. I'll just take a look at the dashboard to see if people are typing. Okay. Okay, I have 1, 2, 3, 4, 5, 6, 7, only 8 people responded. So keep it going. We definitely want to have, there's 22 people, including me here. We definitely want to have more than 8 responses for this one.
I put mine in the chat also.
Yes, I just saw it, and what you wrote was correct.
Okay, thanks.
Huh. I'm really stuck on 8 people. 1, 2, 3, 4, 5, 6, 7, 8. Of course, there's over 10 math majors. So I'm not saying it's only math majors who answered, but we must have at least for this question, we've got to get more than 8 answers. Okay, this is definitely disturbing to me. You know,
Can you see mine?
Those are people. Anyone that's in there, I can see. Anyone who submitted.
Okay,
Who wrote
all right.
anything in there. Okay.
I drew something
You
and
know,
wrote
as a
something.
teacher, as a high school teacher in person, you know, you see the students, you like see their faces, you see they look confused, they look happy, but online, you don't see it, you know, but it's college, so you don't like, it's college. There's a different expectation for a college teacher in that it's not, yes, you want your students to learn, but you know, they have to meet you. they have to meet you part of the way. So there's less of expectation on the college teacher to like really make sure everybody's, you know, with you. Of course, it's I take it pretty seriously, but yes, the answer to this question does end up being 20 degrees because this is the very same trisection construction. If you trisect the segments, so GH is 1/3 of FG, and you draw the horizontal line, you will end up with, if you make a line from A to I, you will get 1/3 of the angle, namely 60 divided by 3 is 20 degrees.
Professor, would you make us actually have to construct the quadratics, or would it be there for us for this type of problem?
It would already be there for you. Now I could, you know, I really like this question. I like that one. So that you're creating at least points on a quadratrix.
Right.
But as far as like trisecting an angle, I would give you the quadratrix already.
Okay, cool. That's what I wanted to know. 'Cause that would be a lot.
Yeah, no, that would. Okay, so that's the quadratrix for trisecting. So if you didn't get this one, maybe you could write me an email or something like, dear, you guys call me Gary. Like, I'm totally lost in this class. You know, these questions that you're saying are really straightforward, are you know, totally, you know, challenging me, and I'm totally lost. So at least I can kind of get a sense of why, you know, because I don't know, is it that people are totally lost, or are they not really here? You know, are they kind of Zoom? Is there a word for that? There must be a word for people who are on Zoom in theory, but not, you know,
Maybe it's
being on Zoom.
ghosting. I don't know.
Ghosting or something. Because
Zoom-
this question was meant to be like, as a teacher, I'm here like, you know, trying to get all this history of math and just the right amount of stuff and just the right difficulty level and questions and all. But when I see only 8 people getting this question, it makes me concerned that on this final exam, I'm going to see the 20s, you know, that I see from time to time, but like more of them. Because this is your real straightforward question. Okay, I don't want to do guilt trip. I mean, it's my job to make sure people are doing well, and I might have failed in doing that, but you know, it's hard. I'm doing this online, remote. I'm giving all the resources I can and all the opportunities to type questions in and all. Okay, so that takes care. Yes.
I'm not sure if I'm the only one who like does Desmos on my phone, like while I follow along with the lecture on like the tablet or computer or whatever. Sometimes on the phone screen, the submit button is like out of view. So like right now, like I've like, as you were saying, oh, only 8 people, like I was reminded to go and like check and make sure that I actually submitted it.
I see.
But I'm certain that
I got you. Okay.
times when things don't get submitted.
I don't think you have to submit though. I think you can just type anything.
Oh,
and
it doesn't,
just comes
it'll
up.
go through anyways?
Yeah, because I see like stuff typing, like as it's typing, I see like text appearing one letter at a time.
Okay.
But maybe.
Okay, I just wanted to check. Thank you.
You're welcome. Okay, so we have spent all of today so far on trisecting the angle. But that's only one of the 3 problems of antiquity. Well, the quadratrix can also be used to square the circle. And here's why. There is a property of the quadratrix. This length, I call it the foot of the quadratrix. We will not prove this. I will just tell you that the foot of the quadratrix, the length here, is always 2 times the circle's radius over pi. In other words, in this case, 20 over pi. Just going to tell you that. So if you actually had a quadratrix, you would have a line segment that pi is like involved in. Now, this is very cool and great, but it's also a bit disturbing. And here's why. Here's my quadratrix. Imagine I want to make that line segment. So here I am, I've gone down by like 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, 70 degrees, 80 degrees. I can get these lengths. Remember, Scott, you asked about the horizontal, GH?
Yep.
I can measure that length with a ruler even. But look at what happens. I'm getting close, but look at what happens. Right when I get to the spot to get the ultimate point on the quadratrix, look what happens. We don't get it. Because see, the lines intersect, they intersect, they intersect, they intersect, they intersect. But when you get down to, you've gone down all 90 degrees, at that point, both of the lines end up horizontal, and we don't actually get an intersection point. Think how frustrating that is. Over here, I have the intersection points because they're not both horizontal, but because the radius is going around and the line's dropping at the one critical point, the spot where I get the magic point that lets me square the circle, the two lines intersect with each other. So you might say, well, how did I know where H was? Because I cheated. I made H 2r over pi. I cheated on that. That's not officially an intersection because those two lines will intersect each other in all places because they're both vertical lines at that point. So right before I get to the magic spot, the lines intersect because one's horizontal and the other one's not. But at the point where I get to the magic spot, the end, they actually they don't intersect technically. They're just the same line, and we can't actually find that point of intersection. So this is really very theoretical because you can make a quadratrix with a compass and a straight edge, point by point. You can make any point you want. You can't make the whole thing, but the only point you can't make is the most important one, the point at the very end. So I'm telling you that if I ask this question on a test, if I give you the radius, the side of the square, you do 2ab over pi, and that will tell you the length of the foot of the quadratrix. That's just a thing that we'll memorize. 20 over pi is about 6. That makes sense. It seems like it should be about 6. So if you thought it was AB over pi, that would be 3. That looks, it's definitely bigger than half. So 2AB over pi. Now check out this picture. Here I have a circle with a quarter circle inside of a square on the right. And I have a quadratrix already drawn. Over there. AJ is the magic number. I'm just going to call this R, and I'll say AJ is 2r over pi. N is the midpoint. So AN is just r over pi. See, I got that N here. That's just the midpoint.
Of AJ, right?
Of AJ. Now, on the side, I make this little triangle over here. That triangle has R as one of its legs and has AN, which is r over pi, as its other leg. Now, if I make another line segment that's perpendicular, or continue this line and put another R here, and then I make a parallel line from that R, parallel to the other hypotenuse. So I have a second right triangle now. The little one has legs r and r over pi, short leg. The big triangle has r as its short leg, and its small leg I'll call x. Now using similar triangles, because these are similar triangles, we got alternate interior angles, and we also have the right angle. We can say that in the small triangle, the big leg over the small leg is equal to, in the other triangle, the big leg over the small leg. And if you cross multiply, you get r squared equals r x, I'll say r over pi x. And then if you multiply both sides by r over pi, you get x equals pi.
Wow.
Which means if I were to make a copy of this triangle over here, the height would be r, and the width would be pi r. So what would the area of that rectangle be? I'll just have someone call it out.
Pi r squared,
Which is?
the area of the circle.
Yeah. So this rectangle has the same area as the circle. And if I were then to square that rectangle using the squaring of a rectangle construction, I would accomplish the squaring of the circle.
Can you just walk through that? That's a lot that you just threw the calculation. Please, can you walk through it one more time?
Do you mean the part, the similar triangles part?
Well, I got to where you had the foot and the r or r over pi, but the derivation of it.
Here you go. So how about let me make the picture a little bit bigger here with less stuff on it.
Okay.
So there are three things we know. This is r, that's r, and this little piece here is r over pi.
Okay, got that.
And I'm curious, how big is this other leg? So similar triangles, these are similar triangles, because remember I made these parallel lines. So there's a lot of alternate interior angles. So these are similar triangles. And there's similar triangles where I know two legs of the small triangle and I know one leg of the large triangle. So I can say r over pi. That's like the ratio of the two sides of the small triangle.
Yeah.
Will equal, in the other triangle, those two corresponding sides. R was the big leg of the small triangle.
Gotcha.
Question mark is the big leg of the big triangle. R over pi was the small leg of the small triangle.
Yeah.
R is the small leg.
Okay.
Then I cross multiplied. R squared equals r over pi times, I'll call it x. Then I multiply both sides by pi over r.
Pi over
which
r.
I didn't show that.
Yeah, I think that's what threw me off. Got it.
So the pi over r cancels out on the right-hand side, but just the r cancels out on the left-hand side. And that's why this length was pi r, and this rectangle was pi r squared. And then when I square the rectangle, that square will have the same area, also be pi r squared. So the quadratrix got its name because, in theory at least, if you could create a perfect quadratrix, which you can't, you could create you could create every point on the quadratrix except the one that matters most. But if you could make this construction and you would square the circle. So, it becomes like, okay, if we could just make a quadratrix, we could square the circle. So it becomes like another problem that math does that a lot of. There's each thing builds on the thing before. So if we could get like another question that's equivalent, or that then we just start focusing not on squaring the circle, but on trying to locate the foot of the quadratrix.
So just to summarize, the rectangle equals the square equals the area of the circle.
That's right. That's right, because the rectangle was pi r squared. It had a height of r and a base of pi r. But that couldn't have happened without
The foot.
without the foot. Without that foot, that's the problem. Making a line segment of length r over pi, there's other ways to square the circle, but this is my favorite of the ways. But we can't make that point. So that's our first squaring of the circle. Here I made another, and actually for this one, I have just another configuration that's pretty much the same, just kind of rearranged a different way. Let me see if I could find that. Cube root doubling the square. Yeah. Over here, quadratrix. Refresh the page. So if I come over here, I like the one that I showed you, but I realized that the one on this page is like slightly different. Let me just bring it up. Hold on, it's a little slow to load up sometimes. Okay. So in this one, same deal. But in this one, instead of making that small triangle, r and pi over r, I just left it. I just basically connected A to the midpoints. And then I made the parallel line so that this rectangle was the square, was equal to the circle's area. So it just had a little bit less. I mean, I kind of like the other one because there's too much going on in this picture. And this one doesn't have the square either. It doesn't have the squaring of the circle. So that's just another, in case you look at that and you're wondering, this doesn't look like this picture.
So that
Yes?
rectangle equals the area of the square, because that looks so much bigger.
No, the rectangle has the area of the circle.
Oh, okay.
But I did not, it's kind of equivalent to, this rectangle. But I didn't go through the step of squaring it, of making the actual square in that picture. I like this picture better. I feel like you could learn better from this picture.
Yeah.
Okay, where are we now? We did that. Oh yeah. Okay, hold on a second. Let me copy this. The spiral of Archimedes can also be used to square the circle. But it's going to rely on a fact about the spiral that I haven't told you yet. Let me come over here. Archimedes spiral to square the circle. Now I mentioned you can't even make a spiral. You can make points on a spiral, but there's no way to make a perfect spiral. So you're not going to be happy to hear that this one depends not just on a spiral, but the ability to make a line tangent. See that? It's a tangent line. It just grazes that. So Archimedes says that if I have a spiral and I have the ability to make tangent lines, which none of those are possible or easy to do, but it's all like in theory. He said these tangent lines are going to be really useful. That's what he says. Check this out. I have a point on the spiral randomly, just a random point on the spiral. I connect A to C. And then I make a line perpendicular to AC. And that perpendicular line ends up hitting the tangent line somewhere. there is a relationship between the length of the perpendicular line, the bigger leg of the bigger leg. I mean, it doesn't have to be bigger. Yeah, it seems like it's always bigger. There's a relationship between the length of the bigger leg and the circumference of the circle. Notice when I go all the way around, the length of the bigger leg is exactly the circumference of the circle.
Right.
Now, you might say, well, what if it's not all the way around? Is there still some kind of relationship? And the answer is yes. When it's halfway around, hold on. Hold on, let me say it this way. The more general relationship, so you can make a note though that when we get to the very end, hold on. When I get to the ultimate tangent line, that line will be equal to the circumference. Of course, once you have the circumference length, you could do the same thing as we did before. We can make a rectangle, and then we could square that rectangle. This is a rectangle with the circumference 2 pi r as the big side, and I did r over 2 as the small side. So its area would be the area.
Where did you get J from to create the width of the rectangle? I am.
Oh, I'm not up to, yeah, I'm getting towards that. Oh, Jay, that was that here. Let me come over here. Let me go back to the iPad now. So the big fact for us is that Archimedes figured out that if you could actually make this spiral, which is already its own problem, and you could make this tangent line, that this line segment, EJ is where J is where the tangent line at the end intersects with the perpendicular line. So that this triangle actually has area is 1/2 2 pi r times r, which is pi r squared. Then I did something kind of funny where I made a rectangle by taking the midpoint. That rectangle is also pi r squared because it's r over 2 times 2 pi r. I think for this class, that's the fact I want you to know. But I just want to mention, and I'm not going to ask you to use this fact that I'm about to tell you, but I want to just kind of, you might say, well, what? That's kind of crazy. How would he know
Professor,
that?
can you go back to the last slide when you're done talking? Sorry.
Yes. So more generally, what Archimedes showed was that this AI line, see, it gets bigger, it gets bigger, it gets bigger. The other one gets bigger also, but the big leg gets bigger and bigger. It turns out that that leg is always the length of whatever this arc is. That arc goes from the point where the tangent line to the quadratrix is. You see that? Point C, it's the tangent point. If you make an angle and make a small circle, that arc always has the same length as this straight line. So the bigger, as I move C out, that arc gets bigger and the line gets bigger until eventually the arc gets so big and it's going to a bigger point that it becomes the entire circle. I'm not going to have us, for this class, I'm not going to have us do the more general question, which is like, what's the length of JE? it's not that it's a bad question, but well, it's actually not that hard. Maybe I should tell you. It only takes a second, so maybe I should show. JE. In this configuration, JE is going to be the same length as, take the point of tangency and make a arc of a circle. Now, how big is that arc? Well, we don't know, because we don't know the radius of the circle, which I'll tell you is 12. And we don't know the angle, which I'm going to tell you is 120 degrees. So here's a question for you now. 3 questions. 1, what's the length of IE? That one's not a hard question. What is it? 120 degree angle, 12. Same question as before. Now this is the same question I gave before when I did the spiral. No tangent line or anything, just like here's an angle. Huh?
It's
It's the
4.
exact question. It's 4. Remember
Yeah.
way back when we did it over, it's one of the first questions we did. It's over here.
Right,
Okay,
'cause
so
you're taking
remember that question.
120. You're taking 120 out of 360. Then you multiply.
That's right.
by 12.
That's right. So IE is equal to 4. Now, if IE equals 4, IE is also the radius of this kind of smaller circle. So the circumference of circle E, of little circle E, is 2 pi times 4. IE is the radius, which is 8 pi. But the blue arc is not the entire thing. The blue arc is only a portion of that circle. What portion is it?
1/3.
Yes.
Yes. Well, I'm telling you without any proof that JE will also be that. If you like formulas, the formula would be theta over 360 theta over 360. I'm going to go like this. 2 pi times theta over 360. That's the big circle, and then times another theta over 360. If you like formulas, that's your formula. If you like the concept is the arc that goes from here down to the horizontal is equal to the length of JE. If you really like formulas, you could say 2 pi and then pi over 360, theta over 360 squared. I personally don't like that as my formula, but I like the concept, because on a test, you know what I do sometimes on a test? I give you a spiral and I say, if this arc is 2 pi, or if this arc is equal to 1.5 pi, what's the length of this line segment? And the answer is 1.5 pi. In other words, I want you to know that this line segment will always equal this arc. So knowing this formula might be good if I say how long is the line segment. But if I tell you the line segment, you know, the different things I could ask. So let me bring up this picture again, because it got kind of ugly. Okay, so the rule once again is that JE is the same length as arc I'll say K, where IK is on a circle, smaller circle. And the arc is from here to here. So the radius of the circle is small because the angle's not 100, the angle's not 360. And then the portion of that circle is also small. That's why we get pi, 2 pi. The radius is, well, we have to know what EI is, so I'm gonna call this R. The radius is theta over 360. Did I leave off the R?
I don't know. I'm so lost, Professor.
Well, I need to have an R in here because the formula for the area of a is, I need an R here. Remember how the radius was 4? That's the pi over 3 theta over 360 times R. That was the 1/3 of 12. Imagine I just gave a question like this. Imagine the question was just, imagine you were in 8th grade and I said, here's a circle with radius 4 and the angle from here to here is 120 degrees. And my question was, what's the arc length? Imagine that was the whole question, nothing else. Well, the arc length would be 120 over 360 is 1/3 of the circle, but the circumference of the circle would be 2 pi r, which would be 8 pi. So the whole thing would be 8 pi. So this piece would be 1/3 of 8 pi. So arc AB would be 8/3 pi.
Yeah.
So this is like 8th grade question. But I understand when I put it in the context of this spiral of Archimedes, it seems like a much more difficult question than it is. So you should study this question first and make sure you're real comfortable with this question. And then we switch over to this picture. And now they're not asking me about an arc. They're asking me for this line segment. But if you know that that line segment is the same length as the arc of the circle that starts here, and here's the entire circle, and goes from here to there, and you're told the angle is 120 degrees, and that the big radius is 12, and the angle is 120 degrees, you go through the same question. The question is still, and you have to know that this line segment is equal to this arc. But at the end of the day, the question is the same question. What's the length of this arc, which I'll call IK?
Yeah, I've been wondering where K is the whole time.
Oh, K is on the horizontal. K is where this little circle crosses the horizontal radius. So it's hard, but honestly, it's just it's not so bad. I mean, yes, this stuff could be overwhelming, these rules, but that's what we're learning about. You know, I teach this stuff to you know, the ninth graders at Stuyvesant, and yes, they're very advanced 9th graders, but still, that you know, it takes studying. So sometimes it comes easily, and sometimes you have to stare at it for a couple of hours. You know, there's nothing wrong with staring at something for a couple of hours. Once you get it into you and you understand it, you'll understand it for the test. That you don't have to say, well, some kid at Stuyvesant as a 9th grader does it, figures it out in 15 minutes. That's not, you're not going against them. You're challenging yourself. And it's true, it might take a lot of staring at this. That's what, you know, that's what studying is. You have to stare at it. And I didn't prove this theorem. I just told you it's just a fact that these two things are equal. So at least we don't have to like try to prove. It's very hard to prove that fact. I just said it's just a thing that's true. If it helps you, you can come over here and fiddle around with it. And I actually have, see, show arc. Oh, it's the whole circle. So I actually have here what arc they're talking about, and that might help you. This black arc is the same length as this black line. Now, when I make it all the way to the end, See, the circle that it's on gets bigger and bigger until ultimately it ends up as the whole circle. So I'm taking the circle is the size of the original circle, the big one, and the percent of that circle is 100%. So that's where that comes from. Okay, so I'm gonna stop here, even though there's one more thing. So tomorrow, so here's the deal. Tonight, ideally, although you don't have to, I put up class number 13 also, which is I made a video that's 17 minutes long that teaches you the algorithms, but I also made a long, like a 90-minute version that shows you where it comes from. It's up to you. If you want to just say, okay, I'm happy, I'm so overwhelmed, I just want to know how to do it for the final, you watch the 17-minute video. If you want to really understand it more deeply, you watch parts 1 and 2 of the video. If you are one of the math majors, you are watching parts 1, 2, and 3 of the video. Part 3 is quite an endeavor, actually. That's why the math majors aren't having to do a final project. They have a really, really difficult question coming, solving a 4th-degree equation with a method developed in the 1500s. So math majors, I don't envy you. Math teachers, you've got 2 things to do. The homework that's due on the homework that's due tomorrow, which is homework 12. Sorry, which is homework 12 is due tomorrow. Homework 13 is not due. Sorry, homework 11 is due tomorrow. Homework 12 and 13, and homework 14, which I'm teaching lesson 14 tomorrow. Those are due on Monday. You do not need to know lesson 13 to understand lesson 14. So you don't have to, if you don't have time tonight to look at that video, that's fine. You just look at it over, you have a 3-day, Friday, Saturday, Sunday to catch up on that. Okay, so I'm going to stick around now.
Professor, I have a comment to make. So there's a difference between productive struggle and people being lost completely. It's a lot to process, and the fact that it's a lot of things. Like Scott, there's other people in the class. I appreciate that you're like asking questions, because I know some of us have had taken the time to try to figure things out, but rushing through and then like saying, oh, stare at it a few hours. Some of us don't have a few hours to just sit and look at the work. We want to be able to see the stuff clearly and to the point, so that we understand what the why is and we can learn from this, because I would like to be able to take this information and turnkey it into something that I could actually use in the classroom for my students. So I really wanted to say that, because I've gotten increasingly frustrated and angry since we've been on this Greek session, because there's a lot of information and it just seems like it's all over the place. And I don't like feeling like that in the classroom. If I was a student in the classroom, I would have already given up. I wouldn't do the work. It just reminds me of some kids that I've seen, some students that I've taught that have given up completely because of stuff like this. So I really wanted to get that out of my system as well, because it needed to be said.
I understand. I have to jump into this. Pacing has been 4 times the pacing of the Babylonian math, and I am so lost, Professor. I'm disoriented. I challenge you to get a neutral party to look at your video of the last 2 or 3 days and compare it to what you did the first week. It is exponentially bigger, faster. I am overwhelmed. And what's the point of just throwing this at us? I know you're behind schedule, you lost a class, but it's so unfair. I
didn't really lose a class. That class is this 17-minute video. So no, I did not lose a class.
I've taught on one concept, and you're throwing 3 and 4 concepts at us. And honestly, visually, it's overwhelming, this stuff. My blood pressure is through the roof. I'm trying so hard. I can't even keep up with you.